So before recalling what we did last time, well, we went through the graph container algorithm of Kleiman and Winston, and then we started application on counting intersecting families, uniform families, the counting version of Erdős-Corrado, and then we start talking about hypergraph containers informally and give an explicit example of a type of container theorem for hypergraph container theorem for triangle free graphs. So let me start today's lecture by giving you an exercise to try to try to use the Kleiman-Winston's graph container theorem yourself. So here's the exercise. Today's lecture 10. The exercise is about counting independent sets in regular graphs. So now we are working with graphs in which every vertex has the same degree. Let me turn on this. So this theorem that I will leave as an exercise was proved earlier, was conjectured by Granville and proved by Noga alone in the early 90s. So here, this is conjectured by Andrew Granville. Then that the conjecture is every n vertex d-regular graph G, then the number of independent sets in such regular graph, I use I of G for the number of independent sets, is at most 2 to the 1 plus little 1 times n over 2. No more than this quantity. So as I said, this is proved by along in the early 90s as yes, well, true. He proved it. This is true. And the bound he proved, he can even give some estimate on this error term, little o1. So what he proved is such graph I of G is at most 2 to the 1 plus. The error term is something like d to the negative 0.1 times n over 2. Okay. There might be some constant here. And the exercise I leave for you is an improved bound by Shapotenko. Who improved this estimate to 2 to the 1 plus some constant times, instead of d to the 1 over d to the 0.1, he can prove 1 over d to the 0.5. So square root d roughly, log d over d. Okay, so this is the exercise. Use Kleiman-Winston's graph container theorem to prove this bound. Okay. One remark is when we see such a result, as I repeatedly mentioned, when we see a result, we always ask, is this best possible? So here we see we have 2 to some power. Well, forget about this error term. Let's just look at this. It's cleaner. We have n over 2, basically, the asymptotic behavior. So we want to ask is this best possible? And the it is. This is easy to see because this n over 2 in the power optimal. Simply because, well, if the graph is bipartite, then we have independence number of G. You can split the graph into 2 parts. Each part is an independence set. So independence number is at least n over 2. Now, by taking all subset of these largest independence sets, we get that I of G is at least 2 to the alpha of G, which is 2 to the n over 2. Okay. We cannot improve it. In some, so when you're far away from being bipartite, we can improve it. This is a different story. We might talk about it later. For now, that's all we need to know. Any question about the exercise? Okay, now let's coming back to previous lecture. Let me copy what we have. So this is the informal version of oh, do I want to? Yes, okay, why not? Give me a second. Okay. Now, here's where we at last time. The informally hypergraph container, let's review how it looks like. We have a uniform hypergraph where the edges are nicely distributed, whatever that means. And well, what it means actually is for the codegree of every subset of vertices, they are not too large, sort of regular. Then we can find a family of containers, a subset of vertex sets, family of subset vertex sets, which can serve as containers for independent sets. This is the first item. Every independent set is containing one of these containers. The second item is we don't want there to be too many containers. Otherwise, we just simply take the family of all independent sets. Trivially, this is a collection of containers, but there are too many of them. So the number of containers, there are very few of them. And the third one is we also don't want the container to be too large itself. Otherwise, you can just take the whole vertex set V of H. There's a single container. It contains all independent sets, but it's useless for us. So the third one says each container, it's small in the sense that it's almost independent set itself, meaning the number of edges induced on this container is there are very few of them. And the last item can often be combined with some sort of removal lemma to get an upper bound on the size of the container. So here's an explicit example we've seen. For the family of triangle-free graphs, we build this auxiliary, we phrase these triangle-free graphs as independent sets in this hypergraph where the vertex sets are complete graphs on m vertices are the edges there, and 3 vertices, which are 3 edges in the complete graph, form a hyperedge if they form a triangle. So the independence set in this hypergraph corresponds to triangle-free graphs on 1 to n. Now, this is what one-to-one correspondence here. This is independent set is containing this container. Every triangle-free graph is containing one of these containers, a family of graphs here. And there are not so many containers. Well, the family of graphs that contains triangle-free graph is 2 to the roughly n to the 3 halves, which is, you can just use even weaker bound, 2 to the little of n squared. But later, in some cases, we need a stronger estimate. For example, transference. Sometimes we want to prove some random analog of some classical results. Now, the third one corresponds to the third one here. Every container is almost independent. Here, our property is not being independent, it's being triangle-free, so we are almost triangle-free. Quantitatively, the number of triangles, triangle density is 0, little of n cubed triangles. Then by triangle removal lemma, which says that if you have little n cubed triangles, you can remove little n square edges so that the remaining graph is triangle-free, which by Mantel theorems is at most n squared over 4 size. So together, a plus b at most n squared over 4 plus little o of n square edges. Okay. Now, we use this to prove this Erdős-Kleinman-Rothschild theorem that the number of triangle-free graphs is 2 to the is basically 2 to the this number, an extremal number for triangles. That's the application, a simple application. Now, let's talk about a special family of triangle-free graphs. We've seen this Erdős is it Kleitman and Rothschild? I believe so. Oh, wait a second. There's one more remark I want to make. There's one more remark. Another remark is, and sometimes we can get the weak type of container theorem from regularity lemma. So we can also rephrase regularity lemma as a sort of container theorem. This is a remark I want to make. From Samarity's regularity lemma. What does this mean? Okay, what this means is that for every triangle, so we want to contain every triangle-free graphs on n, right? So here's the process, how we can construct the collection of containers using regularity lemma. You fix a triangle-free graph on m vertices. Okay. Now what we do is we apply regularity lemma. We get a partition, right? This is the reduced graph. Maybe it looks like this. Reduced graph R. Okay. Now, one thing to notice is that Give me a second. So actually, regularity lemma, we can even get a container for almost triangle-free graphs. But anyway, it's enough for us to get just containers for triangle-free graphs. So we have a graph G, which is triangle-free. If we use regularity lemma, we get a reduced graph. Then we know that the reduced graph must also itself be triangle-free. Okay, so R is triangle-free as well. For otherwise, by counting lemma, G has tons of triangles, positive triangle density. Okay, so what's the size of the reduced graph? The size of reduced graph is constant. Only depends on this epsilon precision. And so that means the number of choice for R is also constant. Okay, for every such constant, you blow it up into a container. So for such R, you blow it up. You choose a partition of the vertexes of G, you take its blow up, complete blow up. And that the number of partition is definitely 2 to the little o n squared. Probably 2 to the big O n, because you just choose vertex sets, right? So you choose some epsilon n, then 1 minus epsilon n choose some epsilon n and just multiply. And the number of terms here is just constant. You partition the vertex into number of vertices into a number of parts, which is number of vertices in R. Okay, which is definitely this. I'm being very generous. Now we obtain. This is not quite yet a container. This guy contains most of G. What are the edges that are not contained? What are the edges in G that's not containing here? Those may be between sparse pairs, and those may be between irregular pairs, right? So all edges. So all except all edges except those between sparse pairs. This is the first type, or irregular pairs, or the third type, the edges inside here, which is negligible, or those inside VI, okay? And are contained in the blow-up of R. So all but this negligible amount of edges are contained in here. That means you can just sprinkle n square, little o n square edges over these to get the container, okay? So we can add little o n squared to each such blow-up of R to get a family of containers for triangle free graphs. Okay, there are little o n squared such edges. So let's compare. Here, well, since this blow-up is triangle free, sprinkle a little bit edges does not increase triangle that much. So still we satisfy 3, satisfy 1 with a slightly weaker estimate on the number of containers. So you can get almost the same family containers, except that we have weaker control on how many containers you have because of the last stage of sprinkling to make sure that all edges of G are contained here. Okay. The family of 2 to the little o n squared containers. This is the remark I want to make. Now, I would like to talk about a very closely related problem. Instead of enumerating triangle free graphs, let's enumerate a proper subfamily, the family of all maximal triangle free graphs. So here, in the lower bound, 2 to the n squared over 4 for the number of triangle free graphs on n. What we're doing is you just take this, you take subgraph of this, right? All subgraphs. But all these subgraphs, except this guy itself, is not maximal triangle free. They are not maximal. So here's the definition. Just remind you, a triangle free graph on n is maximal if you cannot add edges to it, so to remain being triangle free. Okay, none of this, its proper supergraph is triangle free. If adding any edge will create a triangle. This is another way of saying it. All right. It's not maximal. So it's natural to guess, since most of these are not maximal. Is it true that the number of, so recall, the number of triangle free graphs on n is 2 to the 1 plus little o 1 times n squared over 4. Then a natural question is, what about the number of maximal triangle free graphs? Is it much less? As it turns out, it is exponentially smaller. This was asked by Erdős, whether there are significantly fewer maximal triangle free graphs. It was first proved. It's proved by Balog and Petrichkova that there are exponentially fewer maximal triangle free graphs. Here, let me first give you a construction. Still, they are exponential in n squared over some constant, meaning maximal one. So how can we generate many? So let me first give you a lower bound, which is at least the number of maximal ones is at least 2 to the, instead of n squared over 4, we can get at least n squared over 8. So how do we obtain n squared over 8? Let's try to generate maximal triangle free graphs. Here's what we do. Let's split the vertex sets into two parts. Each of size, let's say for simplicity, 4 divides n, yeah? So here's n over 2, an even number. Here's n over 2 vertices, even number. Good. Now, what we do first, construction. In the first step, let's put in a perfect matching in the left-hand side. Let's call it X. Here's Y. So we have a perfect matching. Okay. So put the n/4 matching in X, a perfect one. And we're going to leave Y independent. So don't do anything for Y just yet. Good. This, by this, I mean for every maximal triangle free graphs we're going to generate, they all contain this perfect matching. This is what I mean here. Now things start to differ. We're going to generate different ones. For every pair of an edge in X and the vertex in Y. Okay, here's example. We have two choices to add this edge or this edge. You cannot add both. You're going to create a triangle. We're going to add exactly one of them. Add exactly one cross edge. So for example, if you add this one, then you're going to leave this one empty. Okay, the same for the others. For example, this one and this vertex, you add one, you leave the other one empty. You can do either way. So for every such pair, we have two choices, right? And also easy to see that adding these cross edges do not create a triangle. It's still triangle free. Now, the final, and that's it. The final remark is that some of this way of adding cross edges might not result in a maximal triangle free, might not be maximal. But the thing is, the X-Y cross edges, they are sort of saturated in the sense that you cannot add any more cross edges. All the cross edges is of this form. It's between some vertex and some perfect matching, right? And if you add any more, you're going to create a triangle. So if some of this graph after step 1 and 2 is not maximal, you can add edges inside to make it maximal. They necessarily would be extended to distinct maximal triangle free graphs because they can be distinguished by looking this cut. There's no more edges can be added at this cut, and all these cuts are distinct. So I will not write the last item. So they might not be maximal, but can be extended to maximal. Okay, blah, blah, blah. Maybe let me write it. And extend them to maximal triangle free by adding edges inside X or Y if necessary. Okay, how many such graphs we generate? There are two choices here, and the number of pairs is n/4 times n/2 here, which is n²/8. So we have 2 for each such. This is it. Any question? So for quite a while, there's this exponential gap. Obviously, this guy is at most the total number, 2 to the n²/4. But it's at least 2 to the n²/8, where the truth lies. Where does the truth lie? We don't know. So about 10 years ago, we finally know that in the power, it's actually the lower bound is closer to the truth. Asymptotically is optimal. So this is proved by it's 2014, maybe about 10 years ago. So Pollock and Petrichkova showed that the number of maximal triangle free graphs on N is 2 to the 1 plus little o 1, 1/8 plus little o 1 times N squared. Okay. So the lower bound is closer to truth. Exercise. I will leave exercise to prove this. Okay. Another remark is that this statement was strengthened later. Remember, above the counting results, when you go beyond the counting results, you can even try to describe a typical member of a maximal triangle free graph. Namely, among all maximal triangle free graphs on N, if you uniformly random pick one, can you say something about its structure, a typical structure? And we can prove that as most of these maximal triangle free graphs, they have roughly n squared over 8 edges, as in this construction. Namely, to be more precise, you can, for almost all such maximal triangle free graphs, you can find the partition into two parts of its vertices, such that one part you see the perfect matching, the other part you see independent sets, and you have edges going across. Necessarily, they must have one, exactly one for every cross pair to be maximal. Okay, so this is by Pollock, myself, Petrichkova, and Marian Sharps. So typical structure. I'm not going to say more about this, but instead, I will talk about a closely related problem in additive numbers in combinatorial number theory about sum free sets. So this is all I want to say. All I want to say about triangle free graphs and maximal triangle free graphs. Any question? So let's now, since we're talking about graphs under subgraph inclusion, these maximal triangle free graphs, let's take a slight detour to talk about maximal independent sets in the graph. With count here. In this, at the beginning, we gave this exercise to count the number of independent sets. That's all the independent sets, not including the maximal ones. Not the maximal ones, right? Right. Wait a second. Something is strange here. If we take so what I want to say here is that I think here D needs to be sufficiently large for this to be true. Let me double check. The reason being, okay, the reason being, if D is not sufficiently large, then the graph can be disjoint union of triangles, n over 3 of them. Then there, how many independent sets are here? Well, from each triangle, you can take nothing, or you can take one of these vertices, 4 choices, right? Okay, and you have this many. So you have 4 to the n over 3, which is 2 to the 2n over 3, which is obviously exponentially larger than 2 to the n over 2. So, but this graph is too regular. Degree is very small. So probably here I write everything, you see, D, some function of D. Probably we need D needs to be sufficiently large. That's correct. Good that I noticed. So here, sufficiently large D, okay? And this is little o1 goes to 0 as D goes to infinity. All right. Good. So here we count all the independent sets. Similarly, but for example, if you look at bipartite graphs, let's say complete bipartite graphs, how many independent sets? Well, you have this guy. You can take all its subsets, 2 to the n over 2, but most of this is not maximal independent sets under set inclusion. The maximal ones just 2, one here, one here. So a lot fewer. What about, can we give an upper bound on the maximal independent sets in the graph? This is what we're gonna talk about next. Counting maximal independent sets. So for this problem, first such a result by Moon and Moser, who proved that for every n-vertex graph, the number of maximal independent sets is at most 3 to the n over 3. This is in the 60s probably. For every n-vertex graph, G, the number of maximal independent sets of a graph once again, maximal in terms of set inclusion. You cannot add more vertices to this independent sets to remaining being independent is at most 3 to the n over 3. This is optimal. This is the graph I gave earlier. You have n over, the graph consists of disjoint n over 3 triangles. In this graph, to take a maximal triangle independent sets, we need to take at least and exactly one vertex from each triangle. You cannot take nothing, right? Exactly one. So one from each. You have 3 choices from each one, 3 to the n over 3. So when you see such results, we're not going to prove this. This proof is by induction and using the fact that every MIS, if you choose V, then you kick out all its neighborhood. Then you look at the rest. In every MIS, if it contains V, then the restriction of this maximum independent set here must also be maximum independent set. You can use the induction. I will not prove this. In this example, we have lots of triangles. Naturally, one might want to ask, if we don't have triangle, can we then improve this bound? The answer is yes. This is proved by Hoyter and Tuza. So we can improve this bound exponentially from 3 to the n over 3 to 2 to the n over 2. This is also optimal. And the extreme example is very simple, just perfect matching. In this perfect matching, you have to choose one, and there are 2 choices. There are n over 2 edges. So 2 to the n over 2. All right. Now, let me leave as an exercise for you to prove. You can use this 2 theorem as black box to prove that sort of a hybrid version. So if for every graph G, n vertices, if there exists a set T such that G with T removed, you remove vertices from T, from G, those in T. How do I write it? G minus T. This just means the induced graph of the graph on the sets with T removed, such that after removing T, this graph is triangle free. Then we have number of maximal independent sets of graph G is at most 2 to the n over 2 plus T over 2. Okay. This is an exercise. Now we're going to talk about a strengthening of this Moon and Moser's results. So in Moon and Moser, we get stuck at this 3 to the n over 3. Forget about the graph being, here we need this graph to be triangle free. I forgot to write. Okay. So we get stuck at n3 to the n over 3. If you look at this example, forget about triangle, but without forbidding triangle, can we improve it? One thing one can consider is this graph is quite sparse. It's too regular. Every vertex at very low degree. What if the vertices, let's say minimum degree or average degree, is very high, and let's say the graph is close to regular? Can we improve this bound? And the answer is yes. Okay. So Moon and this is first noticed maybe by Ilinka and Kang. So Ilinka and Kang noticed that we can if G is almost regular, let's say regular, every vertex same degree, D regular with D sufficiently large, then can improve Moon and Moser to 3 to the n over 6 plus little n. So we can save a factor of 2 in the power. Okay, so what we want to see, what we're next going to prove is a strengthening of this result. So here's a theorem. I used to Bollock myself. Andrew Tregelon, oh no, Marian Sherry resulted, and Andrew Tregelon. So we can relax this regular to maximum degree and minimum degree. They are bounded by a factor. So here's the statement. Let k to be at least 1, epsilon bigger than 0, then maybe I should write it this way. For every epsilon bigger than 0, there exists d, depending only on epsilon, such that the following holds. So what is the following? Well, let k to be at least 1, and G is a graph with maximum degree bounded by a factor of k from the minimum degree. Where minimum degree equals to d, sufficiently large. Okay, maybe the following holds for any d bigger than d0 to be precise, right? Minimum degree is d. Okay, then the conclusion is the maximal independent sets in this graph G is at most 3 to the k over k plus 1 times n over 3 plus epsilon n. So this is just little o n, all right? Main term is here. If you take k to be 1, that means the graph is d-regular. If it's d-regular with d sufficiently large, this is 1 over 2 times n over 3. This is exactly n over 6. It's this result here. The reason I want to talk about this statement is we're going to use it later. And another thing is, this is we can prove it using an idea by Shapozenko. which resembles very similar to what we've seen in Kleiman and Winston. So we can try to do that one more time. So idea is Shapozenko. Here's the proof. Maybe before saying the proof, I will say the sketch of the proof. So the idea is that we're gonna remove high degree vertices, fix. The idea is again the same. Given a maximal independent set, fix them. We think of how we can generate the maximal independent set. So given a maximal independent set I, we're going to give it a small signature. So what we do is we here's all the vertices, where the vertices let's say ordered by decreasing order in its degree. You first pick out vertices that are in I. Some of them. These vertices are in I, in I, in I. The high degree vertices. And each such vertex kick out some neighbors, right? There's some neighbors. So this guy needs to be kicked out. Okay. In the remaining set, this is the remaining set U. What we do is we kick out high degree vertices that are in I and its neighbor. So we do that whenever it's possible. In the final set U, what do we know? We know all the intersection of I intersect U, they are low degree vertices, right? If there's anything that's high degree in here, we do that in the first stage and kick out its neighbors. So we know, first of all the vertices in I intersect U is low degree. Now, we're going to define the set of low degree vertices in U. We consider low degree vertices in U, which includes these. So consider Z in U, which is low degree vertices. And by our assumption, by our execution definition of the algorithm, it contains all the remaining vertices in independent set I. And another crucial observation is I intersect U is itself a maximal independent set in U. Okay, so we can use the Moon and Moses results on U. Sorry, on Z. We can use Moon and Moser on Z. All we need to do, Moon and Moser on Z. All we need to show is that Z is not too large. So why is Z not too large? Because only need Z not too large. This is because, remember, here's Z. Z itself is sparse inside U. Okay, it's a low degree vertices. It's sparse, but our graph is almost regular, remember, meaning with D maximum degree KD. So that means most of the edges incident to Z goes outside. If the graph is completely regular and all edges goes outside, then the complement of the set Z cannot be too large because the bound on maximum degree. If Z is too large, then Z bar is too small to receive all edges sending out from Z. So Z cannot be too large, okay? So sparse, if Z bar, the complement, too small, then cannot receive edges from Z, okay? Most of the edges, most of Z edges at the boundary. Boundary means goes from Z to Z complement. That's the idea. Now we're gonna, this is the idea. Now we implement this idea here. Proof. Okay, let's implement this idea. Well, let's fix a maximal independent set. Let's call it I in G. Okay. Minimum degree D is sufficiently large. Now, we're going to repeat this process. Repeat the following process. Initially, we let V1 to be the whole vertex sets. And at the I step, where I is at least 1, we look at the current set Vi. Is there a vertex in our MIS I that has degree large? By large, we set it to be square root of the minimum degree D. Okay. Choose Vi in capital Vi intercept I. Such that the degree of Vi in Vi, this is the degree of little vi in Vi is at least square root D. And then we're going to update. We're going to set Vi plus 1. So we're going to delete this vertex we choose and all its neighborhoods from Vi to get Vi plus 1 is Vi minus little vi and its neighborhood. Okay. We do so as long as we can remove vertices. The total number of steps. So first, and that's it. This is the algorithm. Now, at the end of the algorithm, how many steps? The first observation, the number of steps, let's call it S. S is at most n over square root D, obviously, because at we start with V1 of size n. At every step, when we update to next set, we remove at least D vertices. Square root D vertices. We remove at least square root D plus 1 vertices, in fact. So you cannot go more than this many steps. If you go more than this many steps, there's not enough vertices to remove. Okay, so the number of steps is small. This is when D is sufficiently large. This is at most epsilon n. Keep in mind. Okay, it's small. Now, good. Now we talk about here that the remaining set be U. Let the remaining sets be U. And we're going to define Z to be the vertices in U that has low degree, where the degree of V in U is less than square root D. Okay? So Z is somewhere in here, Z, and every vertex in Z has low degree in U, small degree. This Z, as we mentioned, must contain all the remaining vertices of I. For otherwise, there exists a vertex here, a blue vertex in I, in the remaining set U, that has degree at least square root D. That means the process shouldn't stop. It should have carried on. So, note that I intercept. So you see, this set we initially removed high degree vertices is kind of like the set S in Kleiman-Winston, and the set Z is kind of like the A in Kleiman-Winston, which contains the remaining set of vertices in independent sets. So notice that I intercept U should be a subset of Z. For otherwise, yeah, I would not write. Maybe let me write one more sentence. Notice that for every vertex in I intercept U, degree of V in U is strictly less than D at the end of the process. This implies, i.e., I intercept U is in Z. The next we need to do is we want to apply Moon and Moser, right? So that means this implies, so thus the number MIS of G is at most. So how do we count it? First, we need to count the number of choices for this V1 to Vs, right? Which is this signature sort of. And remember S, the number of steps is very small. At most. This is sum I goes from 0 to n over square root D, which is S, right? N choose I, multiply. So this is the number of choices for V1, V2 to Vs. After we choose V1, V2, Vs, we know the remaining is in Z. And another crucial observation is, I forgot to say here. Another crucial observation. By our algorithm, I intersect U is a maximal independent set in Z. In the graph induced on Z. So we can forget about the whole graph. We shrink to a much smaller graph Z. This is because at every step, before we forming Z in U, we remove a vertex in I, then we also remove its neighbors. So all the remaining, they are not. This should be clear, right? You remove one, remove its neighbor. So at the remaining, if you are not maximal independent sets in Z, that means you can add more vertices to being independent. Then we can add it because this guy is not adjacent to any of the previous vertices. Okay. Now, that means by Moon and Moser, the number of choices for remaining vertices are here, right? Is the number of maximum independent sets in GZ. So this is MIS. This term is 3 to the number of vertices in G induced on Z divided by 3. Okay? Remember Moon and Moser here. Now, all we need to do is to get the upper bound on Z. Z cannot be too large, and we are done. So we are left to show Z is at most K over K plus 1 times N plus little o n, basically. This, then you plug it in, you will get the desired bound. And the reason is here. Because Z is sparse, most of the edges incident to Z goes to the boundary, which goes to the complements. So this is n minus Z, basically. Its complement is n minus Z. If the complement is too small, so we are free Z is too large, which means complement is too small. But we have bound on maximum degree, it cannot receive this many edges if Z is too large. Proof. Why this is true? Let's count the degree sum in Z. Degree sum in Z is at least trivially minimum degree of G times number of vertices in Z. And this equals to 2 times the number of edges in Z. They get counted twice, plus the edges at the boundary goes from Z to V minus Z. Okay, now what do we know about this guy? Well, in Z, these are the vertices, by definition, degree is less than square root D. So in total, this is the degree sum of Z in U. Basically, right, degree sum of Z in U. I get confused for a moment. So it's at most square root D times Z. Okay, every such vertex has degree strictly less than square root D in Z. Plus Now the edge boundary. The edge boundary will at most, every vertex sends and can receive at most maximum degree in the complement. And if you do the calculation, this implies Z is at most calculation K over K plus 1 times N plus 2N over square root D as desired. When D is sufficiently large, this little n. Okay. Any question? So the reason I talk about this is because Shabazenko's version is very similar. And also we now set up all the necessary things we need to prove a statement about counting results about maximal sum free sets in the integers. So let me introduce this notion. What is the sum free sets? A sum free set in integers so we have a definition. A set of, let's just say the first n integers. Well, okay, it doesn't have to be. It could be an infinite set. A set of natural numbers is sum free if it does not have a solution to the equation x plus y equal to z. In other words, for any xy in S, if xy is in S, then x plus y is not in S. Okay. Equivalent for x. Or you can also say S plus S and S are disjoint, similar. S plus S is the notation that you have element x plus y where x, y is in S. Sum free sets. It's a basic notion in combinatorial number theory. Remember that one of the basic Ramsey type statement proved by Schur is that this is called a Schur triple. Okay. So Schur proved that the Schur triple, they are partition regular, meaning that if you color the natural numbers by bounding number of colors, then for sure you will see a monochromatic solution to that. So this is a Ramsey type statement. For any R coloring of N, there exists a monochromatic solution, monochromatic Schur triple. Now we're going to consider a Turon type problem instead of Ramsey type. This is Ramsey type. Turnaround time means, okay, if we forbid shared triple in our set, if our set is sum-free, how large can it be? This is also known. Let's look at the first n integers. So if S in the first n integers is sum-free, what are some examples? Here are two examples, large ones. All the odds. Let's say n even for now, to be simple. So you have 1, 3, 5, 2, n minus 1. What's the size? N over 2. Another example, you can take the second half interval. Meaning, so this is 1 to n, right? You can take this interval as size again. You can even shift it to the left by 1. So this guy, or shift it to the left by 1, size n over 2. Obviously, it's also sum-free. This is sum-free. 2 odd number adds up to an even number, not in here. This is sum-free because of the space constraint. This is parity constraint. Here, add up 2 number, it's going to be strictly larger than n, so it goes outside. Easy. This 2 happens to have size n over 2. I'll leave as an exercise to show that you cannot go beyond that. The maximum size is n over 2. So, exercise. Every sum-free S in n has size at most n over 2. Now, what are we doing? We're doing counting problems. When you see the extremal results, naturally you want to say, if we enumerate them, how many sum-free sets are there? There are. Well, you can take all subset of the odds, and you can take subset of the second half interval. You'll get 2 to the n over 2 many. Turns out this trivial lower bound is optimal. It was conjectured by Cameron and Erdős, and Green independently Shapozenko proved that the number of independent sets is up to a constant factor 2 to the n over 2. So by taking subsets, with the examples above, we get that number of sum-free sets in n is at least 2 to the n over 2. Conjectured by Cameron and Erdős and proved by independently Green and Shapozenko. They proved that the number of sum-free sets in n equals to big O of 2 to the n over 2. So this is stronger statement than 2 to the n over 2 plus little o n. Because this is an exponential error here. This is just a constant error in the front. Good. So while asking this question, Cameron Erdős also asked the question of maximal sum-free sets, as in the triangle-free and maximal triangle-free business. We can ask the same. Most of these sum-free sets generated, most of these are not maximal sum-free. So is it true that the number of maximal sum-free sets are significantly fewer There are much fewer of them. In particular, Cameron and Erdős asked, they're exponentially fewer. Exponentially fewer maximal sum-free sets. Okay. This was answered positively by, so before doing that, let me first, yeah. So this is a positive answer by Wojciech and Schoen. So yes. Wojciech and Schoen prove that this number is at most 2 to the n over 2 minus some constant. This constant is so small, 2 to the negative 28 times n, a very, very tiny constant. It is exponentially smaller. This was improved by Wolfowitz, who showed that this is at most 2 to the 3n over 8 plus little o(n). So much more reasonable constant here. Improved from 0.5 to 0.375. Now here's a lower bound construction originally given by Cameron Erdős of 2 to the n over 4. Give 2 to the n over 4. Let me give this construction. There are two constructions, in fact, so I'll give two construction. Construction 1, construction 2. Okay. In the first construction, let's again assume 4 divides n. Why not? It's going to only affect lower order term. In the first construction, well, let's always, in the first step, always take element n. So n, we're going to put it in all the sets. We're going to construct some presets. Now, by doing so, n is even if we pair up 1 and n minus 1. 3, we look at the odds. 3 and n minus 3. 5 and n minus 5, so on and so forth. We pair up the odds. What does it mean, pair up the odds? Between this pair, two elements in this pair, 1 and n minus 1, we can choose exactly 1. If you pick 2, 1 plus n minus 1 equal to n. This is a sure triple. That's forbidden in some free sets. So we can take exactly 1 element from every such pair of odds. Choose 1 from every pair of odds. Okay, let me not write down the details. And the number of pairs of such odds is what? Well, the odd number has n over 2. Pair them up, so you have n over 4 pairs. Each pair has 2 choices. You get 2 to the n over 4. You generate this many. Similar as before, some of these might not be maximal sum-free sets. You might be able to add some even numbers if it's not maximal, but the intersection with the odd number is saturated. You cannot add more. It's maximal in that sense. So each such extension by adding even number necessarily will yield distinct sum-free sets. So it's at least 2 to the n over 4. The second construction, we pair out things in a different way. We're going to take, so this is n. We're going to take the element n over 4. Now, by taking n over 4, we pair up. Which pair up third and fourth quarters. Pairing up third. What does it mean? The third quarter is here. Fourth quarter is here. What it means is that we now pair n over 2 plus 1 to 3n over 4 plus 1, right? N over 2 plus 2, 3n over 4 plus 2, dot, dot, dot. To the last guy, which is n and 3n over 4. So since we always pick n over 4, between the ends of these pairs, we can pick exactly one of them, not both of them. So choose one from each such pair. Number of pairs, obviously, again, n over 4. This gives you 2 to the n over 4. Maybe you can extend them, but their intersection with the second half is determined, is maximal. So they extend to distinct ones. This is the lower bound. So now if you look at the lower bound and upper bound, 0.25, 0.375, there's an exponential gap. This was closed by Balog, myself, and Treglong and Sharif there. 10 years ago, we proved that this lower bound construction is optimal. In the sense that we add an error term here, this can upper bounds the number of maximal independent sets, which completely settles this problem. So, theorem. This is Balog, myself, Sharif there. And Andrew Treglong 10 years ago, we proved that a number of maximal sum-free sets in N is 2 to the n over 4 plus little o n. And later, let me remark that we improved this same group of people to an asymptotic enumeration. We can actually prove by the residue of n mod 4, it's some constant times 2 to the n over 4 plus little o f 2 to the n over 4. Okay. So running out of time, next time we're going to see the proof of these results using a container theorem for sum-free sets. And some of the tools that we developed today, for example, this bound on maximal independent sets for almost regular graphs, where the degree is sufficiently large. Any questions? Okay, if there's no question, thanks for listening. I will see you guys next. Okay, there's an announcement. Next week is November 5th, right? November 5th, we probably have to move the lectures. I will update the course webpage. The lecture next week on Tuesday will be moved to Monday, let's say. So it will be Monday the same time, November 4th. Announcement here.